Welcome to another essential exam strategy session. Today, we are cracking the code on one of the most notoriously tricky topics in the Cambridge 0606 Additional Mathematics syllabus. We're going to dive deep into this explainer and discover how the simple straight line is actually a powerful mathematical shapeshifter used to decode the real world. Now, if you want to build a blockbuster answer and guarantee top marks, you have to cut the filler and keep the action. Forget basic geometry for a moment. We are talking about a fundamental analytical toolkit that untangles complex data, transforms wild curves, and reveals hidden constants across science and nature. Scene by scene, we are going to build your ultimate exam strategy. Let's get started. Picture this. You open your past paper and you're hit with a complex, real-world application question. For example, before someone takes a bungee jump, how do we mathematically guarantee the rope won't stretch too far and hit the ground? Well, we test it. We hang different loads on it and measure the exact length. Now, I see two types of students tackle this. Let's call them Alex and Sam. Alex overloads with raw mathematics facts, throwing every equation at the page without any analysis of the actual data. Sam, on the other hand, just rushes, panics under the timer, and completely misses the command word requirements. But if you look at the resulting graph, it tells you a story. It gives you the natural length of the rope when there is zero load attached. In the specific case, it's 15 meters. It shows a precise proportional relationship. For every extra 40 kilograms of load, it stretches another 5 meters. This isn't just theory. It is the mathematical certainty required for real-world safety. And more importantly for you, it's the exact logic the examiner is looking for.
To prevent you from making Alex and Sam's mistakes, we are going to build your mathematical toolkit step by step, transforming your red pen marks into green check marks. We'll cover 6 key areas today. 1. The anatomy of a line. 2. Midpoints and distances. 3. Parallel and perpendicular relationships. 4. Power models and logarithms. 5. Exponential relationships. And finally 6. Other linear transformations. Think of this as your personal mathematics success blueprint for acing these graph questions.
Let's kick things off with Section 1, the absolute foundation of everything we're doing today, the anatomy of a straight line.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the foundation. Every blockbuster needs a script, and our script is the equation y equals mx plus c. Let's break down these assessment objectives. Here, m is the gradient, which measures the steepness of the line, and c is the y-intercept, which is exactly where the line crosses the y-axis when x is 0. Think back to our bungee rope, or an experiment measuring the stretch of a spring. The gradient, m, represents the proportional extension of that spring. It's the rate of change. Meanwhile, c is your starting point. It tells us the spring's natural length when the load is completely removed. Examiners love testing if you actually understand what m and c mean in a physical context, not just as abstract numbers.
Finding the equation of a line from a graph is a straightforward 3-step process. But under the pressure of a timer, students mess this up constantly. Think of it like a math version of the Peel framework. Point, evidence, explanation, link. First, your point. Identify the y-intercept, c, by finding exactly where the line crosses the vertical axis. Second, your evidence. Pick 2 distinct, clear points on the line and carefully note their coordinates, x1, y1, and x2, y2. Third, the explanation. Calculate the gradient using the formula, m equals y2 minus y1, all divided by x2 minus x1. It is literally just calculating the rise over to run. Finally, you link it all back together to write your final equation. Top students always structure their mathematical workings this clearly.
Moving on to Section 2. Now that we have the line, how do we measure the space it occupies? Let's look at midpoints and distances.
Measuring the space a line occupies always starts with finding the midpoint. The midpoint is simply the exact halfway mark between the two ends of a line segment. The biggest mistake you can make here, and I see Sam do this all the time, is subtracting the coordinates instead of adding them. You find the midpoint by taking the average. You add the x-coordinates together and divide by 2, then you add the y-coordinates together and divide by 2. For example, if you're given the coordinates 2, 5, and 4, 13, you just average the x values, which is 2 plus 4 divided by 2, getting 3. Then average the y values, 5 plus 13 divided by 2, getting 9. So your midpoint is simply the coordinate pair 3, 9. Easy marks if you don't rush it.
Now, what if the command word asks you to calculate the exact length or distance between any 2 points on a graph? We don't need a ruler. We rely on a classic geometric concept.
We mentally build a right-angled triangle between the 2 points and apply Pythagoras' theorem. The length of the line is calculated as the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. It's a beautifully elegant way to turn abstract coordinate numbers into a concrete, measurable length. Whenever you see the word distance in a coordinate geometry question, your brain should immediately flash a picture of a right-angled triangle. Section 3. Things get a lot more interesting when multiple lines enter the scene. Let's break down parallel and perpendicular relationships. A crucial skill in your Cambridge toolkit is understanding exactly what happens when two different straight lines interact. The rules are simple but incredibly powerful. First, parallel lines will always share the exact same gradient. That means m1 is exactly equal to m2. For instance, the equations y equals 3x minus 7 and y equals 3x plus 2 describe parallel lines simply because they both share a gradient of 3. They will never touch. Perpendicular lines, on the other hand, crash into each other at exactly 90 degrees. Their relationship is a bit trickier. Their gradients are negative reciprocals. This means if you take gradient 1 and multiply it by gradient 2, the result is always going to be negative 1. If one gradient is 2, the perpendicular gradient is negative 1/2. Memorize that rule. It is a guaranteed mark saver. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's dive into Section 4, Power Models and Logarithms, the real shapeshifter. This is the interactive workshop portion of our session, and it's where we transform your potential from an average grade to a top-tier result. We are going to use the straight line as a shapeshifter to tame Wild's curved data. When practical exam questions give you curved graphs representing power models, like y equals a times x to the power of n, you can't easily find the constants a and n. So we use logarithms to literally force the relationship into a straight line format. Here is the transformation sequence. Step 1, start with your power equation, y equals ax to the power of n. Step 2, take the logarithm of both sides. Using your log laws, this expands to log y equals log a plus n times log x. Step 3, map this expanded equation directly onto our foundational blueprint, big Y equals m times big X plus c. Your vertical axis, your big Y, becomes log y. Your horizontal axis, your big X, becomes log x. That makes your gradient m equal to the unknown power n, and your y-intercept c equal to log a. It's an absolute game changer. Let's run a quick data scan challenge. Look at this complex data source on screen. Imagine a 60-second visual timer ticking down in the exam hall. You have raw experimental data for time t and mass y, and it clearly forms a curve. How do you extract the core trend? By calculating their logarithmic equivalents. As you can see in the table, time 4 becomes a log t of 0.60, mass 3.00 becomes a log y of 0.48. By transforming the raw data, that complex, chaotic curve of substance mass over time suddenly snaps into a perfect, solvable straight line. Once we plot log t against log y, we just draw our line of best fit. The gradient and intercept of this new straight line allow us to reverse engineer those original hidden constants with incredible accuracy. This is exactly how you turn a daunting 5-mark question into a simple, step-by-step process. Section 5. We've mastered power models, but what about when the variable itself is in the exponent? Let's tackle exponential relationships and modeling decay. This transformation technique works just as beautifully for exponential models. This is where the variable x is the power itself, like y equals a times b to the power of x. Instead of standard base 10 logs, Cambridge examiners often expect you to use natural logarithms, denoted as ln on your calculator, to unwrap these variables. The steps are incredibly similar. You take the natural logarithm of both sides, which gives you ln y equals ln a plus x times ln b. Once again, you map it directly to our trusted blueprint. Your big y-axis is ln y. But notice here, your big x-axis is just plain old x. Your gradient m becomes ln b, and your y-intercept c becomes ln a. If you can confidently perform this algebraic alignment, you are already thinking like an examiner. Let's look at a classic exam scenario, the cooling coffee experiment. The temperature, represented by theta, drops over time t in a classic exponential decay curve. If Alex were answering this, he'd probably just guess the curve's trajectory, but we use the math. The model is theta equals a times b to the power of t. By plotting the natural log of the temperature against time, that sweeping decay curve straightens out perfectly. Let's do some speed writing mentally. If the y-intercept of this straight line is the natural log of 80, we know the initial temperature was exactly 80 degrees. If the gradient is the natural log of 0.94, we know the coffee's temperature decays by a specific factor of 0.94 every single minute. It's a foolproof system to extract reality from abstract numbers.
Section 6. This is where we bring everything together. Let's look at other linear transformations. This is your universal tool for the toughest questions on the paper. What you absolutely must realize is that this method applies to virtually any complex mathematical relationship they can throw at you. You can map almost any chaotic equation by isolating the variable groups and treating them as simple placeholders, a big Y and a big X, to forcefully create a linear graph. The key to this technique is simply scanning the complex formula they give you and identifying exactly what chunk of algebra to plot on your vertical axis and what chunk to plot on your horizontal axis. The goal is always the same. Leave only the constant numbers as your gradient m and your y-intercept c. Let's do a find the flaw challenge. Imagine testing a relationship modeled as y squared equals a times x cubed plus b for an experiment measuring gas production. If a student's paragraph says, to find constants a and b, plot y against x and calculate the gradient, you immediately know they've lost the marks. The flaw is plotting just y against x, which would yield a weird curve. Instead, to get a straight line, we must plot y squared entirely directly against x cubed. In this scenario, our big Y is literally y squared, and our big X is x cubed. By doing this, the gradient of the resulting straight line directly reveals our constant a, and the y-intercept instantly reveals constant b. Or consider this tricky agricultural yield model. Let's say Ella has a potato garden, and we need to see if fertilizer increases yield. According to the model, y cubed equals a times the natural log of x plus b. Again, we just transform the data. Plotting the cube of the mass, that's y cubed, against the natural log of the fertilizer amount, ln x, yields a perfectly straight line. The gradient is a, the intercept is b. It allows us to extract a highly predictive, linear model from what initially looks like utterly chaotic biological data. This is the highest level of analysis expected in the exam. Let's do a quick cheat sheet recap of our mathematical shapeshifter toolkit. We have 3 rules that guarantee top marks. 1. Command word decoding. Know exactly what distance or equation means. 2. The mathematics Peel framework. Point, evidence, explanation, link for structuring your algebraic steps. And 3, time management, knowing exactly when to use which tool. We've got the y equals mx plus c blueprint, midpoint and Pythagorean distance formulas, parallel and perpendicular rules, and using logarithms to flatten out those tricky power and exponential curves. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Which leaves us with this final thought. If we can reliably use these tools to map the chaotic real world to a simple, predictable straight line, what other invisible mathematical patterns out there are just waiting for the right transformation? Keep practicing, and I'll see you in the next strategy session.